Hi, let's continue now with initializations and why they are so important in neural networks. Weight initialization is a tricky business, and one of the reasons is that there are a few contradictory requirements that we want to satisfy. On one hand, we want to make sure that the weights are not too large, that they're small enough, because if they obtain very large values, then they're quite likely the activations are going to have also very large values, and that this might lead to explosions. On the other hand, we want to make sure that our weights are not too large. They're large enough, because if they're too small, they might yield a very weak signal, very small activations, therefore very small gradients, and slow learning. At the same time, we want to make sure that our activations are more or less centered around zero. This is especially very important for symmetric functions, because the gradients are larger around this zero regime, and therefore we can guarantee better and quicker training. So what is the philosophy behind weight initialization? How do we go about it? How do we decide stuff? The general idea is that weights should be initialized to preserve the variance in the input and the output. So we want to make sure that we've got consistent behavior across modules, such that throughout our hierarchy of modules we still have consistency. We should make sure that the weights are initialized to different values. We should never set them to the same constant value. If we do that, then this means that throughout the forward propagation, all our neurons will here, like in this, like last lecture's example, all our neurons will obtain exactly the same activation values, right, throughout the network. So when we're back propagating, we're going to obtain exactly the same gradients, and therefore all updates will be identical per dimension. This would reduce our effective dimensionality of our neural network just one. That's not nice. Generally, initialization depends on the nonlinearities and the data normalization, or it can depend on it. We have to also understand that bad initialization actually can cause problems. It's not just that it might lead to slow training, but it actually might make things very strange. For instance, if we were to initialize the weights so that we've got constant variance in all layers, exactly the same variance in all layers, I'm not saying that the variance remains constant throughout layers, but we initialize it such that it's constant. This can lead to diminishing the variance in the activation. So if we were to start with activations that are whose range is between -1 and 1, by the 8th layer we might have much smaller ranges of activations. And also, if we were to increase the variance per layer, this can yield exploding activations. Initializing weights by preserving variance is the general strategy, and now let's see what this amounts to. So we have now that our activations equal our weight times our input x, and we want to make sure that the variance in the activations is similar to the variance in the input. So let's compute now what the variances stand for. The variance of the activation is equal to the variance of the sum of multiplications between each individual weight and input dimension. This is approximately equal to taking d times the variance of one of those units, so the variance of wi and xi, so one of those input neurons and the corresponding weight. Now, if we analyze this term further, we find out that it is equal to the variance of the input times the variance of its weight. And the reason is that the expected value for our input and for our dimension is 0. So these terms here cancel out. So all in all, the variance in our activation, in our neuron, is equal approximately to d times the variance in our one of our input dimensions times the variance in one of our weight connections. Now, what we want is to have the same variance in our output and our input, which means then that we can cancel these terms out, and what remains is that the variance of our weight should be 1 over d. Therefore, when we initialize, we should draw random weights such that they've got 0 mean. Therefore, we've got centered weights, and a variance of 1 over d, where d is the number of input neurons in to our layer. When we have a ReLU nonlinearity, however, we've got a slightly different output behavior, right? Specifically for ReLUs, we have the output being set to 0 for half of your input regime here. How does this affect the computations? Well, basically, we can still say that the expected value for our weight, for each of our weight dimensions, is 0, but we can no more say that the expected value of our of each of our input dimensions is 0. It's not 0. So if we do again the same computations, we arrive at finding that we find that the variance of one weight dimension times one input dimension equals to the variance of one weight dimension times the expected value of the squared input here. And if we analyze the expected value of the squared input further, this is an integration since it's an expectation. There's an integration involved, and here we have to note that we make the implicit assumption that we're stacking similar layers and similar nonlinearities. So our input x here to our neural network layer is actually the output of a previous ReLU, right? So then we can replace xi with the maximum of 0, ai. Now there is an overload of notation here because ai is not the output. Normally it would be here the output of our a here of our it's not the output of our transformation. It's rather the input from the output of the previous transformation, but still the computations are basically identical. So for simplicity of notation, we keep the same variable, and then in the end we find out that the expectation of the squared input equals to half of the variance of the output. By redoing exactly the same calculations like before, so the variance of our output then should be equal to the variance of the weight here times, we replace this guy here with 0.5 variance of our output. Now this get cancelled out, so for d dimensions, then our variance of our weight, should be 2 over d. And this is how we should draw our random samples for our initialization of the weights.